Here we have another equilibrium problem. At the temperature of exhaust gases from a particular engine, Kc's value is 4 and 2/10 times 10 to the negative 8. A chemist put 0.085 moles of nitrogen and 0.038 moles of oxygen in a rigid 1 liter cylinder. What is the concentration of nitrogen monoxide in the mixture at equilibrium? As usual, we're going to start with writing out our chemical reaction here. We have oxygen and nitrogen reacting with each other. Both of them are gases. And they're going to form nitrogen monoxide. To balance it, we need a coefficient of 2. From here, we can build our ice table. Break it up into 3 columns, one for each chemical. The nitrogen starts at 0.085 moles, and this time it's a 1 liter cylinder. So remember that the I, C, and E are all in moles per liter. So what that means is that since this is a 1 liter container, the numbers are going to match each other. So we start with 0.085 and 0.038. We're also going to start with the nitrogen monoxide at 0. Nothing is said about it. That means that it starts at none. The only things put in the container were the chemicals that are explicitly listed here and here. Okay, then we need to figure out our change. We know that nitrogen and oxygen, they have the same coefficients, so they're going to decrease by x. But we do notice this time that their starting numbers are different, so their equilibrium numbers will be different as well. We're not going to be able to get away with just using a square root like we did last time. The change in the nitrogen monoxide, however, it will be positive because it starts at 0. It can only go up, but it has a coefficient of 2 in front of it, so it's going to be a change of 2x. And its final value is going to be 2x this time as well. From there, we need to write out our Kc equilibrium. Kc is going to be equal to the concentration of the nitrogen monoxide at equilibrium squared, because of the coefficient of 2, times the concentration of N2 and O2. Looking back at our original question, Kc is equal to 4.2 times 10 to the negative 8. Now what we notice about this is that 4.2 times 10 to the negative 8 is a very small number. Our concentrations initially for nitrogen and oxygen are much larger. Question is, are they larger than 1,000? Pretty easy to see if you put it into scientific notation. The nitrogen is 8.5 times 10 to the negative 2. The oxygen is 3.8 times 10 to the negative 2. Don't worry so much about these numbers. Worry about the exponents over here, right? We have negative 8, and both of these are negative 2. So this is a factor of approximately 6 times greater. Right? So this is about a factor here. This is a factor of 10 to the power of 6 difference between these two. That would be equal to a factor of 1 million. That is much greater than rule of 1,000. So this meets rule of 1,000. What does that mean for us? Well, what that means is we can change these two numbers right here. Instead of saying it's going to be 0.85 minus x, because this meets the rule of 1,000, we can round it to 0.85 and 0.38. The reason that we're doing this is that the change of x is going to be very, very small compared to this initial concentration. And we know that because we know that the initial concentrations are over 1,000 times greater than the Kc value. In fact, they're about 1,000,000 times greater than the Kc value. So it's going to be a very, very tiny change. Mathematically, it's going to work out to be the exact same number in the end, whether or not you include that minus x in both of these equilibrium values. This makes our life much, much, much easier when we do this calculation. If I were to do the full calculation, I would have to write out, I should start with my number, not with Kc. I would have to write out 4.2 times 10 to the negative 8 is equal to 4x squared, because remember it was 2x, so the 2 gets squared as well, over 0.085 minus x times 0.038 minus x. It doesn't take a lot to see here that this is going to end up being some fairly complicated numbers, right? We're going to have to end up with a quadratic formula. It's going to be messy. We're not going to like it. It's going to be difficult calculation to do. If we do this, though, with the rule of 1,000s, it becomes much simpler because we only end up with x in one place. So we get 4.2 times 10 to the negative 8, still going to be equal to 4x squared, but this time it's just over 0.085 times 0.038. And like I said, even though this looks like it's going to make a big difference in the numbers, because the change is going to be so small in the end, it actually won't. So let's go through and do this calculation. This time, instead of having x in the numerator and the denominator at the same time, it's only on top of the fraction. This makes it much easier to solve for. We can bring both of the numbers in the denominator over to the other side. Here I'm using e as the short form to save space. Remember, the capital E is short for times 10 to the negative, or times 10 to the power of. So we have 4.2 times 10 to the power of negative 8 times 0.085 times 0.038. That is going to be equal to 4x squared. That then will give us about 1.3566 times 10 to the negative 10 is equal to 4x squared. Of course, we can divide both sides by 4. So we're just left with x squared. And while we're at it, let's add in the square root so we can just finish this off. So we're going to divide both sides by 4. Then we're going to take the square root, and this is going to give us our final answer of x is equal to 5.82 times 10 to the negative 6. And you can see now this is going to be very, very small compared to those original numbers that we started out with. Now, important thing with this, though, is that for the concentration of the nitrogen monoxide, you have to remember that it was 2x. These questions can go on for a little while, so the concentration of the nitrogen monoxide was equal to 2x. So we're going to have to double this. So it'll be 2 times 5.82 times 10 to the negative 6. And once we plug that in, our final concentration is going to be equal to 1.2 times 10 to the negative 5 moles per liter. Rule of thousands makes life much, much easier. Now, you could still do this using the quadratic formula. However, you're not going to have to in Chemistry 30. It is doable, but you don't have to do it on multiple choice questions. So if the long answer were still a part of the Chemistry 30 diploma, this would actually be a valid question where you would have to go through and do a quadratic equation. However, we don't have to do those ever with multiple choice and numerical response. Since there is no long answer anymore on the Chem 30 diploma, you don't need to worry about using the quadratic formula. If you have to use it in Chemistry 30, it means you've forgotten something.